Well, let's talk about half-life, okay? And simply put, the half-life for a reaction is just defined as the time required for the concentration of a reactant substance to decrease to half its initial value. And we can represent that very simply with this vertical bar, this column, and we'll call this 100%. This is our starting concentration. Okay, if I were talking about, let's say, this reaction, I could simply say this represents the concentration at time 0, t equals 0. So if the half-life is 12 seconds passes, and after 12 seconds passes, we have 50% remaining. Now that is one half-life. Okay, one half-life has expired, and after one half-life, we only have 50% of the 100% that we started with. If we allow another 12 seconds to go by, we're down to 25%. So now we have 25%. This is two half-lives, and I'm just going to abbreviate half-life, HL. So now I have 25% remaining. Let's go for three half-lives. And if I started with 100% and one half-life went by at 50%, second half-life goes by, now I have 25%. Well, this is now my new starting concentration, so one of those half-lives, or a third half-life goes by, I've got 12.5% remaining. And then we can just keep extending that. We go to a fourth half-life, and after four half-lives, we've got, what is that, 6.25%, and then five half-lives. Looks like, what is that, 3.125%. Yeah, that seems right. Okay, so there you go. That's our simple definition of half-life. It's just defined as the amount of time required for half the concentration that you start with to decrease. All right? All right. So I'll leave this to you. After three half-lives, what percentage of the initial reactant remains? I will refer you back to the previous slide in your video or your PowerPoint notes. All right, so here we go. So let's take a look at the derivation of half-life for a first-order reaction. So since A0 is the initial concentration, that's our 100% concentration, and then 1/2 of A0, that would be our 50%. So we would start here with 100%. One half-life goes by, we're now at 50% concentration, which is just 1/2 of whatever the starting concentration is. All right, so here's the first order integrated rate law. We can describe or derive the half-life for a first order reaction by simply, here's our A0, and log of A0 times 1/2 will be our A at times t. So this is just going to be log of 1/2 A0, and this just represents 50% of whatever the 100% we started with does, and we're just looking for the half-life. So the natural log of 1/2 A0, and all I did was subtract the natural log of A0 from both sides. So this is just minus the natural log of A0. I subtracted it from both sides, and I wound up with the natural log of 1/2 A0 minus the natural log of A0 is equal to minus KT 1/2. I'm going to go ahead and use my log rules. I can now express this natural log of 1/2 A0 minus the natural log of A0 as a ratio of the two A0. So that gives me A0 over A0, and you can probably guess what's going to happen. Anything divided by itself is going to equal to 1. That's going to give me the natural log of 1/2 is equal to minus KT. I'm going to move that negative sign over from the right side to the left side. Now I have the negative of the natural log of 1/2. And since the natural log of any decimal is going to be any number less than 1 is going to be a negative number, I can express this as a positive value of the natural log of 2. Or you can just take the minus the natural log of 1/2, and you'll get 0.693 is now equal to KT 1/2. And I'll rearrange the equation, and this gives us the half-life equation for a first order reaction. You'll notice that there are no concentration units here, and so that is a unique feature of first order reactions. The half-life for first order reactions are independent of concentration. You should memorize the half-life equation for a first order reaction. Okay, so previously, we determined the value of the rate constant from the slope of the line. Therefore, the half-life can be determined using the derived equation. This guy right here. Okay, you can get the half-life from this equation. So let's solve this example problem for a first order reaction. Now the first thing to recognize that if they didn't tell you in this problem that it was a first order reaction, you could have determined that by simply looking at the units on the rate constant, because it tells you the first order rate constant for the decomposition of a certain antibiotic in water at 20 degrees Celsius is 1.65 per year. Now you don't have to worry about the 20 degrees Celsius. That will be a constant. Remember that the rate constant is going to change if you change the temperature, and it's telling us that this is the rate constant at that temperature. So you can ignore temperature. It's not going to figure in this particular problem. So the first thing you want to think about with this type of reaction, where you have things like a starting concentration, you're given time that expires. The time that expires is 3 months. I'm just going to put those months over here. So that's going to be your time that expires. You have an initial concentration, and you have a rate constant K. So the first thing you want to do is probably just go ahead and write out the symbolic form of the first order integrated rate law, which is going to be the natural log of A times T is equal to minus K times T plus the natural log of A naught. That's the starting concentration. Well, we've got this directly. We've got 6.0 times 10 to the minus 3. So this is going to be the natural log of that starting concentration times 10 to the minus 3. And this is in molarity. And then plus times T. Well, the first thing we want to do here, we'll want to convert this into years, because those are the units of the rate constant. There are 12 months in 1 year. So months will cancel. That's going to give us 3 times 1 divided by 12, which is going to equal 0.25 years. It's a quarter of a year, 3 months. So we can go ahead and we can put that time right here, 0.25 years. And then finally, we've got minus, and we're given 1.65, and that's going to be 1 over years. Okay, and I know it's a little bit messy, but you can see that years will cancel when you multiply the rate constant K times the time in years. And so we're going to be able to get a value for the natural log of A at times T. So when I plug that into my calculator, minus 1.65 times 0.25 plus the natural log of 6.0 times 10 to the minus 3, I get minus 5.53. Okay, now this is not the concentration. You're not going to have a negative concentration. This is the natural log of the concentration at 0.25 years or 3 months. So we have to take the antilog of the natural log. So we'll take the E of both the natural log of A at times t and minus 5.53. Those two are equivalent to each other. And what that's going to give us is the actual concentration at times t, which is 0.25 years, which is going to be equal to 3.97 times 10 to the minus 3 molar. Okay, so that will be our answer.